Okay, today we're going to be looking at Chapter 5, which deals with alkenes, and it's basically our introductions to our alkenes. In Chapter 6, we're going to be looking at the reactions of alkenes, but in this, we're going to introduce and look at some of the terminology we're going to use with regard to those reactions. Alright, but let's start with something that's true of alkenes and other hydrocarbons, and more so, that we're going to be looking into as we get more involved. So first thing we're looking at here is called the degree of unsaturation. Basically, it's talking about how many hydrogens have been removed. It's also sometimes called the degree of saturation because of that. Now, we learned already with our alkenes that generally speaking, the number of hydrogens is twice the number of nitrogen, or twice the number of carbons plus 2. That's where that formula comes from. So we actually use that formula to calculate what we're going to call the degree of unsaturation. Now, the degree of unsaturation typically is just a good reference to tell us if there are pi bonds or rings present. For instance, if I gave a formula of C8H14, we could actually look at the maximum number of hydrogens, which would be 2 times 8 plus 2, or 18, and subtract that from the hydrogens I gave you, 14, and divide that by 2. And you get 2 degrees of unsaturation. Now, those 2 degrees of unsaturation mean that there could be 2 pi bonds, a pi bond and a ring, 2 rings. It's just a combination of that. It doesn't tell us all that much for certain about the structure. Just, gives us a place to start. Now, the biggest reason we're including this in this chapter is because alkenes will always have 1 degree of unsaturation. Alright, so this formula we came up with, we're going to expand on it some. So you're always going to take the number of carbons and multiply it by 2. And you're always going to do that add 2. Now, what we always subtract from this is the number of hydrogens, but technically we're also going to subtract the number of halogens. Because if I replace one of those hydrogens with a fluorine, I won't really change the elements of unsaturation or the degree of unsaturation. I'm just actually changing hydrogens for halogens. So we're always going to combine those. And we're going to add our additions later on because we're going to add in something for the number of nitrogens and even the number of oxygens possibly, because those will happen in there. So we're going to add to our degree of saturation's formula as we get a little bit more involved in this. Alright, but what does it mean? It just gives us a starting point. So C8H14, for instance, we know 2 times 8 is 16 plus 2 is, 18. And if we subtract 14 from that and divide by 2, this molecule has 2 elements of unsaturation. Now, that really could be 2 separate pi bonds. And that's not the only way to do 8 carbons with 2 separate pi bonds. It could be a ring and a pi bond. It could be a pair of rings. It could be a triple bond. So it doesn't tell us exactly what the structure is. It tells us a possibility. And obviously, CaH14, there's a lot of different ways we could put that together, because that's not the only 4 ways. A lot of different ways to do a triple bond with 8 other carbons. Alright, but it's at least a start. Alright, now, nomenclature-wise, we introduced quite a bit of this in 2 chapters ago, and we did actually cover alkenes then, so think of this as a refresher. Now, we know that all of our nomenclature rules change when we have a higher priority functional group, so we're going to make that part of our backbone typically. And in this case, it's easy enough to go over here as our backbone, because that indeed is even though it's a complex substituent, it's one of our more common ones. So we could actually possibly name this as 2-isopropyl. And then 1, 2, 3, 4, 5, 6, hexene. And nothing terribly complex about that. Alright, and we're not really adding to that. If there's only 1 double bond, we just name it just like we did before. We don't need to do E or Z or cis or trans because that's a CH2. So we can name it as simple as that. But when there's multiple double bonds, we're going to add to our nomenclature because it gets a little bit more complex now. Alright, so we still want our double bonds part of our backbone. So on this top one, I am going to zigzag quite a bit on this. And that is definitely a substituent. Numbering wise, we want the double bonds to have the lowest possible number, so I am going to make that the number 1 position. So that methyl's at 2, 5, 6. So full name for this is 2-methyl. Now here's the tricky part. It's a 1,3 hexadiene. Alright, that's not the complete name, because if I come over here and do this one as well, one 2-methyl, this would also be 2-methyl 1,3 hexadiene. Alright, so what is the difference? Well, technically, it's how this double bond is. Now, it is definitely over here, that second double bond is definitely a trans, and that's what we care about. But we really can't use trans anymore because we have multiple double bonds. And we're not just going to use E and Z anymore by itself. We're going to want to talk about what bond we're dealing with. Now, being that this is trans, that's more appropriate to refer to this as an E, because that's low priority and that hydrogen's low priority. We're going to say where this E is. So this is a 3E. Put that 3E in parentheses, and that specifies the orientation of the double bond in that third position. This one over here would be 3Z. And that really is the only difference between those two. Alright, next one down here, they're right back to back. 1, 2, 3, 4, 5. There really isn't a sister trans or E or Z here, because that's just a nice linear molecule. So this really is just pentadiene. And we do need to specify where they're at, so that is 1, 2 pentadiene. Cyclooctadiene, 1, 2, 3, 4. So 1, 3 cyclooctadiene. All right. On to something a little bit more complex. We introduced this last chapter. We're going to actually make sure we cover it again. We are going to number these shortest possible way, right? Alright, but the double bond takes priority. What I mean by that, this is either the 1 position and that's the 2, or this is the 1 and this is the 2. Same over here. 1 and 2 or 1 and 2. That's the only choices possible. That has to be 1 and 2. Alright, the tiebreaker is going to be the other substituents. I can put this chlorine either at the 1 position or the 2 position. 1's better. So we're going to do that. So this becomes a 1,6 dichloro cyclohexene. And there isn't a 1 cyclohexene. That 1's implied because of the double bond. Similar thing happened as over here. This methyl group is either at carbon 1 or 2. 1 is better. And we have an ethyl and a methyl. So we have 5-ethyl, 1-methyl, cyclohexene. The double bond takes priority. And it doesn't get a number because it's part of a ring. Okay, what we're going to see in this chapter and right now is we're going to introduce the whole idea of what a functional group is. Now, we've been using it before as a term to say that's how we choose how to name it. Alright, but why are we grouping things by functional group? Well, we will find as we get into things, functional groups behave very predictably. And what I mean by that, if I know ethylene or ethene reacts with HBr to turn into an alkyl bromide, and it does that with very predictable reaction chemistry, I actually know cholesterol, because it has a double bond in there, will do something similar. The double bond will react the same in cholesterol as it does in ethene. Now, there is more to this than just saying it reacts exactly the same, but it is safe to say that all double bonds, regardless of where they're at in a carbon backbone, will behave similarly. They have a similar function. Now, what actually adds to our confusion is certain functional groups take priority over others, and that's what we're going to group them as. That's what this groups are trying to show. So our simplest group, the ones, and we're not saying they behave similarly. We're saying that these are less reactive than the 2s, the 3s, or the 4s. And even that's a little bit misleading, because we are going to find there are certain reactions that we can do to our 3s very easily, and we can do to 1s very easily. We just use totally different reaction conditions. So we just got to make sure that we understand when we have similar reactions or similar reagents between two different groups, we got to make sure we understand that the group 2s, for instance, would be more reactive than group 1s. All right, how does that translate to something realistic? All right, come back to that just a second. Where's my reaction page? Think about this. So this is a very simple reaction we learned early on in the very next chapter. It's the second one down here. We are going to be able to take almost any alkene, react it with chlorine, and add the chlorine across that double bond without any problem whatsoever. Turns out that same molecule, chlorine, will react with an alkane, but we don't get 2 chlorines added. We get a hydrogen replaced. This becomes a substitution. A hydrogen gets replaced with chlorine. The other chlorine ends up part of HCl. Now we do get mixtures, because technically I have 2 different hydrogens. I could have the hydrogens off that first position, one of those 3 get replaced to make this first one, or one of these 2 get replaced to make this one. And then the H that comes off gets with the other chlorine, makes HCl. So we get mixtures on it, but it is just a substitution. On this one, that's just an addition. They add right across of it, and there is no other products. All right, so what's interesting is the second molecule does have a CH3 and a CH2. That chlorine will never react with them. The chlorine's going to prefer to react with the double bond, because a double bond has higher priority. And when I back up to this little priority chart, I see that our alkenes are higher in priority than our alkanes. That's what they're showing on this. Now, this is a more complete list. We are fine right now just to realize it's the type of bond we're looking at that makes the categories. All of our carbon-carbon bonds are down here low. Now, this says lowest priority, but these are both higher than just a carbon-carbon single bond. But once you go a pi bond, you get a little bit higher priority. If you go to an NH2 or an OH, so an alcohol or amine, higher priority. And then any of our carbonyl functional groups are higher priority yet. But this page shows all of the functional groups we're going to include, even in organic too, and their different priorities. Now, right now I have certain ones in bold. All the ones that are in bold are the ones that we've actually talked about at this point. We're going to expand on it, because this little prefix row is what we're going to use if you use one of our functional groups as a substituent. Like, the double bonds are what we're introducing, but we're going to see we're going to be allowed to put them off of a ring or off of a multiple bond and actually use a name as if they are just a substituent. That's going to come in handy if they are lower priority than something else. Alright, and that's what we're talking about here. Now, the interesting thing is, we are going to see this a lot, especially when you have something like an alcohol on a ring. Because the only way to actually name this as a cyclohexanol would to actually definitely say that's a substituent. That's saying a double bond is a substituent. That's perfectly allowable. It doesn't have to actually be part of the backbone if something else definitely takes priority. And the neat thing is for us is we're actually going to introduce right now how we can do that. So it turns out a CH2CH bonded on it, so what looks like an ethene is allowed to be called vinyl. And even though vinyl doesn't seem like it has anything to do with two carbons, vinyl is an acceptable IUPAC name, so calling this a vinyl substituent does give us an IUPAC name. Vinyl cyclohexane is perfectly legitimate. And another common one is the allele group, where the double bond is next to a CH2. So it's a CH2, then your double bond. So it's like a vinyl with an extra CH2. But that allele group is common enough, it got its own little acceptable IUPAC name. So we have allele cyclohexane. Now, both these do have a different IUPAC name. There is absolutely nothing wrong with calling this cyclohexol and call that's the substituent off of ethene. And even here, we could say 1, 2, 3. So 3 cyclohexol propene. And the propene and the ethylene, I didn't number them because there's only one way that this could be done. That would have to be the 1 position. And over here, this would have to be the 1 position. So I don't need to number them. That's the only way to actually do it. All right. But there's no way to do this as the backbone, because the rest of the ring, we don't really have a name for turning the rest of the ring into a complete loop on the backbone, because that would actually imply an infinite backbone. So in that case, what we do instead always is we end up calling this CH2 just methylene. And methylene gets called a substituent off the cyclohexane. And this one here has a second name, but an easy name for it is to call that a simple substituent. It's chloromethyl. There's also bromomethyl and iodomethyl, but it really is just saying there's a methyl with a halogen off of it. But we could have actually said this is 1 chloro, 1 cyclohexyl, methane. And that would be perfectly acceptable IUPAC as well. You see how much more words that is when we can just say chloromethyl? Alright, so these seem like common name type things, but they're not. They're IUPAC. They're what we use for when an alkene is better to be called a substituent. Alright, when we have multiple functional groups, that's going to happen often, but not always. Like on this first one, there is no reason I couldn't put the alcohol as part of my backbone and the double bond. So that could be my backbone, and that is not a substituent, that's part of my backbone. Alright, what is going to change is how we number it. I have 2 competing functional groups, but if I back up to my priorities chart, I see alcohols are higher priority. So when I number this backbone, I want it to have the lowest possible number, so I'm going to put it at the 2 position. Therefore, this double bond starts at 4. Alright, naming wise, this is a pentene-ol. Has the ene for the double bond, has the ol at the end for the alcohol. And I don't want to just run that all together. What I'm going to do is pent, I don't want that e yet, pent 4-ene 2-ol. Those 2 separate numbers, putting them before the prefix that applies to them, is how we're going to do that. We don't say 4,2 pentenol. It's pent 4-ene 2-ol. So we put the numbers in the name when we have multiple functional groups. Now over here we have a ring. And what's interesting about the ring is going to be our backbone. So we have one of those 2 double bonds as our backbone. This other one is a substituent. Numbering it, we want the alcohol to take priority for the same reason it did over here. So we're going to call that number 1. Therefore, that's 2 and that's 3. All right. The single double bond as a substituent is a vinyl group. So we have 3 vinyl, 1 hexene or cyclohexene, and 1 ol. We are going to number both those. So 3 vinyl, cyclo pent 1 ene 1 all. Oops, I dropped my dash. Now, interesting, if you leave the numbers off, it's implied to be 1 and 1. So this one is perfectly acceptable, and this is the only one that's like this, to say cyclo pent ene all. It's perfectly acceptable to say that. It's just not often done because it has two functional groups in the backbone. Almost always when we see two functional groups in the backbone, they will number them both. Alright, we talked about that. The reason we have these functional groups is it turns out when there is a chemical reaction going on, we can actually narrow it down to how the electrons are behaving. Turns out in all of our organic molecules, the electronegativity difference creates what we call electron-rich and electron-poor parts of the molecule, or atoms. Electron-deficient, we're going to typically refer to them as electrophiles. These are kind of like acids. Matter of fact, H plus is an acid. Now, the reason we don't say electrophiles are acids is because back in general chemistry, we would have said HBr was an acid, and that would have been right. Well, HBr itself is non-electrophile. In HBr, the hydrogen is the electrophile, but this, and I see I got a typo here, that should not be a subscript, that should just be Br. But this Br is actually negatively charged. It's got a partial negative to it. So that bromine is electron-rich. Yet all electrophiles are electron-deficient. Now we will see carbocations pop up. Those are definitely electron-deficient. Anytime you see a positive somewhere in a molecule, it's electron-deficient. We also see boron pop up. Boron's a great electrophile because, especially something like BH3, it's got that incomplete octet, that Lewis structure. Having that spot there is going to create electrophilic properties. We're going to see even Lewis acids pop up. So a metal like aluminum with just 3 chlorines around it, even though that's perfectly stable ionic compound, that empty spot allows aluminum trichloride to behave somewhat like an electrophile. All right, but think about electrophiles as electron deficient, and we're going to typically talk about where that electrophilic behavior is localized. So even on that CH3, CH2, we're not going to say that whole thing is electrophilic. The electrophilic location is right where that carbocation is. That will really help on something like HBr, because HBr is electrophilic, but it's only the H that's electrophilic. Turns out the Br is electron-rich, therefore it's nucleophilic. And if I said electrophiles were kind of like acids, nucleophiles are kind of like bases. Matter of fact, it's safe to say all bases are nucleophiles. And that's OH negative is definitely a nucleophile. A basic amine, CH3NH2, is definitely a nucleophile. Almost any time you see a lone pair, you're going to see nucleophilic properties. Alright, but I did say all bases are nucleophiles. It turns out not all nucleophiles are bases. Because water by itself, which back in general chemistry we found out could be an acid or a base, it's definitely a nucleophile. The electrons on the oxygen are definitely going to be something that's going to behave like a nucleophile. Even a halogen that's got a full complete octet, so a halogen negative ion, that's going to be nucleophilic. But basically it's electron rich. Now what's going to happen, what we are going to find is all reactions that we look at in all of organic chemistry can be broken down into something very simple. A nucleophile will attack an electrophile. Matter of fact, this reaction up here, it's a two-step process. We have a nucleophile, the double bond, essentially attacks the electrophilic hydrogen. Rips it right off that HBr, leaves those electrons with the Br, so these electrons come over here, and we end up with a weird carbocation where the H is attached to one side of that where that double bond was, and the other side has a positive charge. And then we have the bromine that kept its electrons. Well, this second step, we now have another nucleophile, which is the bromine with those leftover electrons. And now the electrophile is where that double bond was, but because it's now carbocation, it's electrophilic. And in this case, now the halogen comes in and attacks that positive. And we get a addition across that double bond. It takes 2 steps, but it's an addition. Now, what I just did was drew out the mechanism for that. The mechanism of the reaction is going to help us understand what's going to happen when I change this initial alkene. Because it turns out alkenes always do this, but some of them behave or react faster than others. So it really depends on what else is on the molecule rather than just the double bond. But understanding that full mechanism helps out. And more importantly, we often do something like this. We will have our mechanism broke down in 2 separate reactions, and we will have reaction arrows drawing where the nucleophile attacks the molecule. And it's really the nucleophilic center. So the double bond is the nucleophile, and it specifically attacks the hydrogen. Those bonds, which represent the electrons, go onto that bromine. So the arrows are very specifically drawn. They're not drawn from molecule to molecule. They're drawn from specific location in the molecule to something else. That's why this Br negative is attacking exactly where that positive is. So our arrows are very specifically drawn, not in general. All right, now on with something else we're going to get out of this. Once we have a mechanism, thermodynamics and kinetics will tell us a lot about what's going on, and we have to take advantage of this a lot. All right, so thermodynamics typically tells us how much of a product is formed. More importantly, it talks about this ratio. If you remember back when we first introduced Ks back in general chemistry, and it's the capital Ks, were the equilibrium Ks, we're really talking about products versus reactants. We would sometimes see there were reactions that really favored for going forward, and we had other ones that favored staying backwards. Well, that's a factor we have to deal with in organic chemistry, because we would like to go forward always, but that's just not always the that's not always how things work, because the direction of the reaction is related to the stability of the products and reactants. We can't change the stability of them, so we have to take advantage of other things. Our kinetics really talks about how fast it goes, and these sometimes work against us. We can't always say that reactions that favor products are always fast or always slow. These are 2 separate things that we will need to be working on manipulating. All right, so let's talk about what we're going to see here. Well, it turns out when we actually look at a given reaction, understanding what's going on in the transition state or in the middle of a thing is very helpful. And we've kind of looked at that even on this simple reaction we did already. So I took an alkene, and we were going to eventually turn it into a haloalkene. But we knew up here at this very first transition state we were going to have a carbocation, which is kind of interesting because it's a carbon that would actually have just 3 bonds in an empty spot. Something we talked about in general chemistry never happens. Well, that's why it's so high up here in energy. But understanding the nature of that carbocation can understand how we can actually stabilize that high point, and why certain ones are more stable than others. More importantly, why certain carbocations are more stable than other carbocations. All right, but by studying that transition state and what it actually looks like, we can actually see a lot more. Now, something that's actually going to be kind of nice for us. Turns out the transition state is always related to the reactants and products. It's somehow related to both of them simultaneously. All right. The other thing we're going to have to factor in when we start looking at this is the overall thermodynamics. Now, when we actually introduced this in General Chemistry 2, we did a lot of math on this. Right now, we're actually going to focus more on what's the nature of that arrow. Does it favor going forwards or backwards more? And we're actually going to have to realize that there are sometimes competing reactions that do the exact same opposite thing, but they give us totally different products. Maybe it's E and F. And they both have their own equilibriums. Sometimes E and F is more favored than C and D based on various different conditions. But the stability, that thermodynamic stability, is going to help us figure out what product is actually going to be made in the larger amounts. All right, now where that distinction comes from typically is related to the stability of the reactants and products. And that's something we introduced even back in general chemistry with a term called delta G. So most Ks that were larger than 1, ones that favored making products, did so because the products were lower in energy. Matter of fact, that first reaction we showed, where we have a double bond, and over here is a something with a halogen on it, that's lower in energy. It does actually favor making products. Now, what's kind of interesting, later on in this semester, we're going to take that halogen that we just made right here, and we want to know how to turn it back into an alkene. And there is a way of doing that. We just can't do it quite the same way because it's an uphill process. We're going to actually end up making something that's less stable. We actually have a reaction that favors going backwards over forwards. But we can actually study that. Now, the Gibbs energy listed on here, and even this next page that shows us actually calculating, makes it seem like we're going to be doing some math. Now, we kind of are sometimes. This thing down here is how we actually got a delta H. And if you remember from general chemistry, we never actually really got the delta G's too easily by themselves because they were so darn temperature dependent. Well, we could actually get the delta H's and delta S's by looking them up in tables. And that's what they're doing here. They took that same reaction we've been looking at, that double bond with HBr, and then we've added the H and Br there, and they've done a bunch of gathering up the data, and they figured out that that particular reaction is exothermic by about 22 kilojoules, or kilocalories. Alright, the reason we won't need to do this math as often as it seems is because, see how this says right here, pi bond of ethylene is 62 kilocalories? Well, I can mark out this of ethylene and put this approximate, and that's kind of true. Almost all pi bonds have about 60 kilocalories per mole. So these other things don't really affect it all that much. They change it some, but they don't really actually overall affect this. And we can almost safely say this approximately 22 kilocalories of exothermic reaction happens anytime you take an alkene and turn it into an alkyl bromide. Almost dead on every single time. Now there are going to be things that affect it, but what changes it, it changes it here on that little last digit. It goes up and down by a few tenths. But for the most part, you can safely say these reactions are always exothermic. Now, something else we can say, we really don't need to actually estimate or calculate our delta S. We will find out that in almost every single one of these reactions, there is going to be a decrease or an increase on entropy based on what's actually happening. Like the reaction we just had, we had two reactants become one product. And it's kind of safe to say that would have to be a decrease of entropy because we have fewer molecules. And the fewer molecules reduces our entropy. Alright, but it's such a small factor in all this. The delta H is always a very large factor in this that you will see later on in our chapter. We never even talk about delta G after this chapter. We don't even really talk about entropy. Anytime we do any math to tell if a reaction's favorable or not, we're going to only pretty much look at the delta H's because that's going to be the driving factor for every single reaction in almost all of organic chem, and the entropy never really factors in. Even when we do the opposite, reversing this reaction where we know the delta S would probably be positive, it's such a small amount that the delta H sign is what controls the reaction. And we can really just ignore the influence of entropy. Alright, but the nice thing is, we will do some math on this, and we will look at it when we're going through the chapters and we're doing some of the stuff in the chapters. But I never do any of this on the test because it's safe to understand when you have a general idea that an alkene reacting in HX to become a alkyl bromide, if you understand that's an exothermic reaction, it's always an exothermic reaction regardless of what alkene you use. So we don't really need to actually understand the actual value of our delta H's or delta G's to understand what's going on. We just need to know in our class as a compound if it's a favorable reaction. And when it's unfavorable, we want to understand how we can get a control over it. Like some of those where we have a delta G that's actually positive, so kind of like an endothermic type reaction, we're going to find that solvation, the solution it's in, will help us out a lot. We can actually affect our entropy and our enthalpy just by what else is in there, in the beaker per se. All right. First one I want to look at that's a kind of a factor in that actually helps understand some of this is the hydrogenation of an alkene. So hydrogenation is just a fancy term that says we're going to add hydrogen across a double bond. It even happens when you're cooking with oils. So as you probably are aware, oils and fats are things that we have in our cooking supplies, and oils typically being liquids are liquids because they have double bonds in them. As we heat them up, we hydrogenate them, and we actually get those double bonds to go away. Well, in the petroleum industry, they do this all the time because while butane exists and other alkenes exist, they're not necessarily the best fuels. They get way too hot. So if I could actually somehow make that double bond go away, I've now made butane. So this hydrogenation is a very beneficial thing. Problem with hydrogenation, it requires a lot of temperature. Without a catalyst, we're talking about 300 degrees Celsius on the low end. And I just said this is very flammable. Would you really want to heat it up to 300 degrees? No. Especially on the industrial scale, the crater it's going to leave behind if it lost control is just ridiculous. So the catalyst lowers that. And what this particular catalyst does, and the PD is palladium, the carbon is embedded in there. So we actually call this poisoned palladium. But the palladium is just a group of atoms, and the hydrogen comes in here, and it actually kind of sticks to the metal. It actually breaks the hydrogen bond. So the hydrogen is actually bonded to the palladium catalyst. Well, the palladium and the carbon keep the hydrogens at almost the perfect position that when the alkene comes in here, it basically, one of these H's will attach to that pi bond, and almost immediately the other H will attach to it. It's not simultaneously, it is two separate steps, but we get the H's added across very, very rapidly, and it takes care of that double bond. Well, this includes quite a bit of cool things into us. So this hydrogenation is going to actually help us understand that there are different strengths on different alkenes. Turns out butene, being that there's two of them, there's two butene and there is one butene, they behave very differently in this. Now they end up making the same thing. Both of those, when we do catalytic hydrogenation, you end up with butane. Just one of these is a heck of a lot easier than the other. And it really, if you think about it, if you think about what this is going to do, doesn't it make sense if I have hydrogens here as opposed to carbons, that it's going to go in a little bit easier? Think about that. If that's a C and that's a CH3, those are going to be in the way. And that's exactly what kind of happens. The other things off the double bond get in our way and slow the reactions down. I mean, look at this. So I have a bunch of different butenes with a single methyl on them, and the only thing we've done is move where the double bond is. Got the double bond in between on the chain, to the left of the chain or to the right of the chain. But more importantly, if you look at what the double bond has, that top one, off the double bond is a carbon and a carbon and a hydrogen. On this one here, I got two hydrogens here on the left because it's a CH2, and on the other side of the double bond is a carbon and a carbon, a CH3 and then a CH2 CH3. And then on the bottom one, look how it being all the way on the end. On this left side, on the right side, I have hydrogens. On the left side, I have this isopropyl group, but then I have an H here. Alright, but look what happens. I have three hydrogens there. It takes quite a bit of energy by comparison to break that apart. Yet here, with just one hydrogen, it takes a little bit less. Now, it's not a huge difference. We're talking about 4 kilocalories. That's like 4 food calories. This is not a big energy difference. But it is enough that we can actually say, this one must be a little bit less stable. What do I mean by less stable? Well, let's look at those on like a graph. That least stable is higher in energy. And we know stability is lower in energy. And being more stable, we actually didn't get as much energy out of it when it broke down, because it was more stable to begin with. But it's actually going to create a nice little rule. We're going to actually be able to say later on that a double bond, an alkene, is more stable based on the groups coming off of the double bond. Nothing else really. Doesn't matter really on how many carbons there are in the entire double bond. It's just how many carbons are coming off that double bond. Alright, now when we talk about speed of a reaction, turns out speed of reaction really doesn't have much to do with reactants and products. At least not directly. Reactants and products talking about stability tells us how much one's going to be favored than the other. This delta G is related to how they're shoved together, what the two look like. Alright, so what do I mean by that? When I have a transition state that's easy to form, I typically have a fast reaction. When I have a transition state that's hard to form, I typically have a slower reaction. And it really doesn't matter if it's endothermic or exothermic. The height of the hill affects the rate. Alright, so what affects the height of the hill? Well, it turns out the stability of the transition state is what we're looking at, or what it looks like. So, I know both these say delta G. Typically we see this, the kinetic stability, superscript to the delta G is this little crosshair thing, which does say transition state. Matter of fact, we will see Lewis structures drawn. There's my Lewis structure. Remember how when we did cations and anions in general chemistry, put them in brackets and then put positive and negative? Well, now we're going to do that and put a little hash mark on there to say that's the transition state. Very common thing we look at. We will do these Lewis structures of transition states a lot because knowing how painful that molecule is to get put together or how unstable it is typically tells you if your reaction is going to be fast or slow. Now, other ways that we can speed up a slow reaction is really temperature. Because when we heat something up, it does two things. It obviously gets the molecules moving faster. That does two things for us. When they're moving faster, they're going to increase their collisions. So that increases with temperature. And the energy in the collisions would increase. So both those two factors would increase with an increase of temperature. And we're going to see that's often a factor. Matter of fact, if we need to increase the kinetic product or something we know forms fast, we actually can use temperature to help control that sometimes. Alright, now other things we can pick up from the rate, a little bit more versatile than just understanding that they are affected by temperature. Turns out if we actually know a rate law, for instance, if we knew a reaction has a rate law like this, we know for sure in that slowest state, the only thing that's important in that transition state is A. And that really does mean first order reaction, and on that hill where that delta G is got that weird little double hash mark, this thing is just a modification of A. That transition state looks just like A. It's just something different about A that's ever so slightly different. If you have a rate law that has two things, you know that transition state is somehow a combination of A and B. It must be. Now, in both cases, those are unstable intermediates. But we know a lot about it if we know what's in that molecule. We know what that transition state involves. It's going to help us out a lot. Alright, so equilibrium constant, we will talk about this some, and we will list values. But generally speaking, we're going to list values that say favor product or favor reactant. So a large K or a small k. We will talk about it more like that rather than a numerical value. And that really is showing us overall forward or reverse reaction. But we deal with this a lot because there is going to be very few reactions where we say we only get the product. They're almost always at equilibriums. And even worse, there's always a situation, or most of the time, where you have more than one product. B prime. So they'll be similar, but they're going to be put together a little bit different. What I mean by that Notice how we've been talking about this double bond reaction with HBr. Oh, that's not what I need to have a plus there. And we said, well, it just adds HBr across that double bond. Well, what if there's a CH3 on just one side? Do we have it where the CH3 is just on that same side like we just drew it? Or is it better to say, or is it the other way, opposite? You see what we've done there? Still HBr added across the double bond, but I'm saying, did the H add here, and then the Br over here, or did the H add here, and then the Br over here? Because it's still HBr. Both are possibilities. So, do we get just one? Do we get both? Do we get one more often than the other? They are both more stable because they're both alkyl halides. So both these products have an arrow favoring going forward. But does one favor going forward more? That's going to help us with our equilibrium and understanding what's going on. But we're not going to do it with regard to math. We're going to relate it to the actual structure itself when we do our mechanisms. That's what we're going to be looking at, is what do these transition states look like? Because it turns out the transition states and understanding what's going to go on is going to help us predict stability. Now, what we're seeing on this so-called reaction coordinate diagram, it's that mechanism for a double bond with HBr that we introduced at the very beginning of the chapter. But rather than just show what we've made in drawing the arrows, we've drawn what they must be looking like in three-dimensional space, or at least tried to, as a neat weird Lewis structure. So remember, back when we first talked about this, we said the nucleophile attacks just that H, and then this bond comes up here. Well, this is showing the proximity. So we've redrawn it so this HBr is near where it's going to attach. And we just chose one of those two H's and drew it directly over one of those H's. And we're going to show that partial bond that's being formed. And we're also showing that that double bond is being broke as this bond's being formed. And we're showing this bond's being broke. So we have partially formed bonds and we have partially broken bonds. But it's showing what is all going on, and we just put the little brackets in there and say transition state. It's not a stable molecule. We don't ever see hydrogen making two bonds. But it's actually showing how the arrangement of the atoms must take place, or how the collisions are, for this reaction to go on. And that's the same thing that's going on the second step. Before we showed the bromine attacking. Well, instead of actually drawing the arrow, we're drawing the transition state where the bromine is literally right there, and we're showing that new bond forming. Now, where this really pays off, if we think about this, isn't this quite stable by comparison to that first transition state? Yeah, because if you think about it, this bromine's forming a bond. Almost looks exactly like our final product. Yet here we have a hydrogen trying to do two bonds. We know hydrogen doesn't like to do that. And we have a carbon that's going to end up with just three bonds. And we know carbon doesn't like to do that. So this transition state is highly unstable. It's actually taking something that was relatively stable and makes something that's totally unstable. But we see that when we actually do our diagrams. So that first step shows a huge amount of activation energy, or a very unstable transition state. And it shows a slightly unstable intermediate. But the intermediate didn't take a lot of energy, because the intermediate was already an unstable carbocation. Putting that unstable bromine into it did actually take some work, but once we got there, we get all that energy back. So much more small step. But altogether, we get this crazy cool little reaction diagram that shows this two steps, the two separate reactions, two separate transition states. Show that our original reactants turn into those intermediates, and those intermediates finally turn into our products. And we will see we're going to do this type of thing for pretty much every single reaction that we look at throughout all of organic chemistry, because if we understand what's going on with this one, we can kind of predict what's going to happen if I got rid of one of those and just had an unsymmetrical double bond. Alright, last little thing we'll introduce is catalysts. Now, at first when we do catalysts, we are going to use them just to speed up reactions or to make them flat out possible, and we will talk about their mechanisms, how they affect it. And they almost always do something slightly different. What I mean by that, there are ones that actually catalysts that actually bond to our reactants and create new intermediates totally. And sometimes they just create a single intermediate. But they actually do all the same thing. Every single catalyst, regardless of how it happens, lowers the activation energy. We say enzymes here because there's a chapter later in your book where they're talking about catalysts in general and a lot more terminology with regard to catalysts. And we find out enzymes, the proteins that actually speed up chemical reactions in our body, kind of use every single catalyst technique that we know of simultaneously. And for instance, the digestion of a protein, I can do it in the chemistry lab. If I were to take a big huge chunk of steak, for instance, and throw it into a beaker with some pretty strong acid and warm it up, I could actually reduce every bit of those bonds and turn that steak into a bunch of protein molecules. Then we'd separate it all out, etc., etc. It'd take about 24 hours. Yet, if I isolate the digestive protein from a mammal, the enzyme, and just get that enzyme up to around 70 degrees, 70 to 90 normal body temperature, it can do the same job in about an hour. So ridiculously fast because the enzyme is an incredibly cool catalyst. All right, but we'll be doing more of that, and we will be doing this type of thing over here with all the catalysts that we introduce, even the hydrogen for that catalytic hydrogenation that we introduced earlier in this chapter. All right, that gets us ready with some of the terminology. Almost all the terminology in the end of this chapter will be used totally in the very next chapter. So if you are one of those people like I was, that having the examples really help out, you will see every aspect that we cover in the end of this chapter in the very next chapter when we're doing reactions with alkenes.